Let us start the discussion on metal and metallic alloys. Here we'll start with the ferrous metals and their alloys, and that means the steel and cast iron. Objective in this lecture is we'll see what are the different types of metals and alloys, and then different types of steel, their structures and applications, and finally we'll see the cast iron structures and their applications. Now, as you can see, metal alloys can be divided into two major groups, ferrous and non-ferrous. Ferrous means where base metal is iron. Again, ferrous can be classified into two major categories, steel and cast iron. As we have already seen in our phase diagram, steel means if the carbon percentage is less than 2% carbon, and cast iron if it is more than 2%. On the other hand, in a non-ferrous, there may be aluminium alloys, copper alloys, but in this particular lecture we are not going to cover that part. Now, the steel, which is basically less than 2% carbon, that can be divided into two categories. One is the low alloy steels and another one is the high alloy steel. In the low alloy steel, basically if the alloying elements are less than 10%, then we call it a low alloy steel, and if the alloying element is more than 10%, then it is high alloy steel. Okay, now this low alloy steel can be of two kinds. It can be either plain carbon steel or it can be of low alloy steels. Okay, that means the alloy steels. So carbon steels can be of low carbon steel, it can be medium carbon steel, or it can be high carbon steel. That you can see, if it is carbon percentage less than 0.25%, then it is low carbon steel. If it is between 0.25 and 0.6, medium carbon steel, and high carbon steel is 0.6 to 1.4. Now each of them, suppose this low carbon steel where the carbon percentage is less than 0.25, this can be plain carbon steel or it can be low alloy steel. That means if the alloying element is not there, then it is only plain carbon steel. But if alloying element is there but the percentage of alloying element is less than 10%, then this low carbon steel can have its alloy, low alloy steel, which is called high strength low alloy steel. We'll see that in detail afterwards. So low alloy steel, each of these can be divided into plain carbon steel and alloy steel. So plain carbon steel means only iron and carbon is there. Okay, and according to the carbon percentage, they can be low carbon steel, medium carbon steel, or high carbon steel. But each of them can be either plain carbon steel, that means other than carbon almost there is no other alloying element, or it can be low alloy steel, that means the alloying elements are limited to 10%. On the other hand, high alloy steel, where the alloying elements are of a large amount, you can see more than 10% alloying elements are there. Those can be of two kinds, either tool steels or stainless steels, and we'll see their different categories. Okay, so if we recapitulate our iron carbon diagram, if you remember, you see this is the portion where the eutectoid reaction takes place. So this portion is basically the portion of steel, right? And to be very specific, that up to 1.4% is basically what is the steel, but 1.4 to 2% is basically ultra high carbon steels, are very limited use of experimental purpose. This kind of special structure can be formed, but mainly the mostly used steel, commercially available steel that we use, are in the range up to 1.4% carbon. Okay, on the other hand, you can see the cast iron region in the diagram. It is basically 3 to 4.5%. Though we have told that if it is more than 2%, it is all the cast iron, but mostly which is practically used, the cast iron grades, R carbon percentage in the range 3 to 4.5%. Okay, this thing you have to remember. Now coming to the iron, we know that iron is started 3000 years ago and continues till today. Okay, and carbon forms an interstitial solid solution when added to iron to form steel. The atomic radius of carbon is very small, that is why those carbon can go into the interstitial space within iron. Okay, and you can see there are different electrodes of iron, those are present already. Some of them you are very much familiar with, like alpha iron up to 770 degrees centigrade, you know it is ferromagnetic and PCC crystal structure. Then from 770 to 912, probably we have not specifically mentioned in the phase diagram this beta iron, which is paramagnetic. That means the magnetic property is feeble, a very small magnetic property is there, which is BCC crystal structure. Not very remarkable, and very small amount is there within that small temperature range. Then 912 to 1394, it is the austenite range, you know, FCC crystal structure. And 1394 to 1530 is the delta iron BCC crystal structure. We have seen all these, almost all these structures in our normal phase diagram. These are all interstitial solid solution of iron with carbon. Okay, now if we want to see that how from the iron ores how steel is prepared, here there is a schematic diagram where you can see the iron ores are taken from the mines, and after preparation of those iron ores along with coke and the limestone is poured into the blast furnace. Here this particular furnace where this pig iron is prepared is called the blast furnace. Okay, so here you can see and during a lot of chemical reactions are taking place within the blast furnace, and because of that some exhaust gases are coming out, and you can see the gases are coming out from the blast furnace in this region. So here basically iron oxides react with the coke in presence of limestone, and ultimately iron is produced, and those molten iron settle at the bottom, and just above it some slag is deposited. And here you can see high pressure air, high pressure high temperature air is forced into the blast furnace to complete the combustion within the blast furnace. Okay, since these are put at a very high pressure, and that is why the name is blast furnace. Okay, the air is blast through the tuyeres, so this is the region. So at the end we get the pig iron out of the blast furnace, but in this pig iron a lot of carbon is still present, and if we have to remove those carbon, what is done, it is sent to the BOF, basic oxygen furnace. In the basic oxygen furnace basically oxygen is supplied, and because of that some of the carbon and sulfur converted into carbon dioxide or sulfur dioxide and removed. Okay, and then it can be taken into a limited amount of carbon that was required for the steel, and we get liquid steel out of it. Or there is another method by which also the steel can be made in the electric arc furnace, where the steel scrap that is poured into the furnace, this electric arc furnace, where some pig iron can also send here, and some steel scrap, those are coming from the scrap yards, coming charged here, and then with the help of carbon electrodes arc is generated at a very high temperature. Finally the steel is produced here, and obviously necessary treatments like the carbon control or other alloying element control can be done afterwards, and we get the steel out of it. So these are the methods by which the steel actually produced. Here you can see some of the basic reactions that takes place within the blast furnace. You can see you can see that how iron actually reduced and iron is formed. Okay, And here you can see how the slag is formed, like calcium oxide, silicon oxide, aluminum oxides. These are formed and settle just over the molten pig iron. Okay, so those slags are basically taken out and can be used for some other purposes. So let us see a video where the idea will be cleared, that how the process of making the pig iron occurs.
Blast furnace. At the end of this module, you will be able to explain the process of extraction of iron, list and describe the various parts of a blast furnace. Did you know the world's first ever metal bridge to be built was the Iron Bridge? It spans the River Severn in Shropshire, England. And that the Eiffel Tower in Paris is made of more than 18,000 pieces of iron? Every day we come across innumerable objects, from nails to skyscrapers to bridges, which are made of iron or have iron as an essential component. Why is iron the most widely used metal? The main reason is that it is strong and relatively inexpensive. Iron is the most abundant metal found in the Earth's crust. As it is a reactive element, it does not exist as a metal in nature, but is found in chemical combinations with other elements such as oxygen, sulfur, and carbon in the form of minerals like hematite, magnetite, geotite, limonite, and others. Hematite and magnetite are the main ores of iron. Ores are obtained from the earth by mining, and iron is extracted from them. Have you ever wondered how iron is extracted from its ore? Iron is extracted from its ores in a blast furnace. What is a blast furnace? How is iron extracted using a blast furnace? Come, let us find out. Let us take a look at the different parts of a blast furnace and study their functions. The blast furnace is a huge furnace used to extract metals from their compounds using a suitable reducing agent. It is a tall chimney-like structure about 30 to 40 meters tall and about 10 meters wide at the base. It is narrow at the top, increasing in diameter downward but narrowing again near the bottom. The bottom portion is called the hearth. It is lined with fire-resistant bricks. At the top of the furnace is a double cup and cone arrangement. This arrangement is used for the introduction of the charge, which is a mixture of coke, concentrated iron ore, and limestone. The furnace has 3 outlets, an exhaust gas outlet at the top for the hot waste gases and 2 outlets at the base for discharging molten metal and slag. The gas discharged from the gas outlet is passed through a dust catcher to remove suspended particles and then fed to the stoves to heat the air that is blown into the furnace. At the bottom of the furnace, there are 2 nozzles called tweezers, through which hot air is blown into the furnace. This process is called blasting, and that is why the furnace is known as a blast furnace. Extraction of iron from blast furnace. At the end of this module, you will be able to describe the working of a blast furnace. Let us now find out how iron is extracted from its ore in the blast furnace. Before the ore can go into the furnace, it has to undergo certain preliminary treatment like concentration or dressing and roasting or calcination. Iron ore mined from the Earth's crust contains impurities such as sand, rocky materials, limestone, etc. The impurities are collectively known as gangue. The gangue must be removed before the metal can be extracted. The process by which impurities are removed from the ores is known as concentration or enrichment. To begin with, the ore is crushed into small pieces in a crusher. The crushed ore is then powdered in a grinder or pulverizer. The powdered ore is then washed in a current of water to remove impurities. The heavier ore particles settle down while the lighter impurities are washed away with the water. The concentrated ore is then subjected to a process known as calcination. The ore is heated strongly in the presence of air in a reverberatory furnace. Besides converting the non-oxide compounds in the ore to the oxide, roasting helps in removing moisture and organic matter. Impurities such as carbon and sulfur are converted to their volatile oxides which escape. In addition, ferrous oxide present in the ore is oxidized to ferric oxide. Let us now see how iron is extracted from the roasted iron ore. The process of extraction of iron from its ore is known as smelting. The roasted ore is mixed with coke and limestone. What roles did coke and limestone play? Coke functions as the fuel, at the same time gets converted to carbon monoxide required for the reduction of the ore. The limestone acts as a flux. A flux is a chemical substance which combines with impurities and forms a fusible slag. The charge is brought by trolleys or skip cars over a conveyor system and introduced into the blast furnace through the cup and cone arrangement. Simultaneously, a blast of hot air is blown into the furnace through the three gears at the base of the furnace. The hot air causes the coke in the lower regions of the furnace to burn, producing carbon dioxide and a large amount of heat. This region is called the zone of combustion, as the combustion of coke takes place here. The temperature in this region reaches around 2000 degrees Celsius. The carbon dioxide rises and reacts with the unburned coke to form carbon monoxide. At the same time, the heat causes the limestone present in the charge to decompose and form quicklime and carbon dioxide. The reduction of carbon dioxide and the decomposition of limestone are endothermic reactions. Owing to this, the temperature of this region falls to about 1000 degrees Celsius. Calcium oxide or quicklime fuses with impurities such as silicon dioxide to form liquid calcium silicate or molten slag. The slag flows to the bottom of the furnace and floats on top of the molten iron. This is tapped periodically into ladles for disposal. Since molten slag is produced in this middle region, this region is called the zone of fusion. The temperature of the upper region of the furnace is around 400 to 700 degrees Celsius. In this region, the descending charge is exposed to the action of carbon monoxide streaming up from the lower part of the blast furnace. Carbon monoxide reduces ferric oxide to iron. The iron so produced is a spongy porous solid. As reduction of iron oxide takes place in this region is called zone of reduction. As the iron descends down through the hotter regions of the furnace, it melts. Lower down the furnace, where the temperature is high, any unreduced core is reduced directly by carbon. The molten iron collects at the bottom of the furnace and is tapped periodically. It is poured into sand molds and allowed to cool and solidify. The iron obtained from a blast furnace is brittle and is called pig iron. Note, the term pig iron comes from the time when the molten iron was fed into molds from a common runner. The whole arrangement looked like a sow suckling its piglets, with the runner being the sow and the molds the piglets. The solid iron ingot removed from the molds were therefore called pigs. The unused carbon monoxide, along with nitrogen from the hot air and carbon dioxide, pass through the outlet at the top and enter the dust catcher, which removes dust and other particulates. The dust-free gaseous mixture is burnt in special burners, and the heat produced is used to heat the air that is blown into the furnace. The processes of addition of charge and removal of molten iron and slag goes on day and night for years. The blast furnace is shut down only when the fire break gets worn away and needs to be replaced.
Okay, so you got a very good idea, I think, that how pig iron is prepared. Now, after the preparation of the pig iron, the steel making process is started, where pig iron can be used to make the steel, or the, I have told, the steel scraps are used for recycling. So here in this video you can get some idea. So the initial part already you have seen.
Process, the fudge is subjected to filtration. The water is recovered and the dry ore is sent to pellet. In hours of baking, the coal is transformed to coke, the basic fuel for the blast furnaces that produce pig iron or first fusion iron. Another raw material for the blast furnaces is sinter, a porous mass. Processed iron and coal, the basic raw materials for produced pellets, and sinter, which are stored in the copper's facility located on the top. Hot air is introduced under pressure into the bottom of the furnace, blasting the coke and smelting the iron ore in an environment of drained through tap holes and troughs and emptied into 200 metric ton capacity torpedo cars. In order to eliminate sulfur content, reagents such as calcium carbide and magnesium are applied to the pig iron in the desulfurization plant. The slag generated during the smelting is deposited in a slag pit to be cooled with water. It is later stored or sold as a byproduct. For the conversion of pig iron to steel, AMSA uses the oxygen-based technique of steelmaking called BOF, Basic Oxygen Furnace, as well as an electric arc furnace. BOF steelmaking begins by loading scrap metal into the converters, pear-shaped refractory-lined furnaces with capacities of up to 150 metric tons lined internally with refractory brick. When the proper amount of scrap metal has been loaded into the converter, molten pig iron is added by means of large ladles operated by traveling cranes. For refining, oxygen, argon, and nitrogen are injected into the mix under pressure through tubes known as lances connected at the top and bottom of the converter. After a period averaging 45 minutes, liquid steel is obtained. The steel is poured into large ladles and ferroalloys are added in order to adjust its chemical makeup to match the requirements of the material ordered by our clients. Production of liquid steel by means of the electric arc furnace is conducted by beginning with a mixture of scrap metal, iron briquettes, or liquid pig iron at a rate of 150 metric tons per casting. Scrap and briquettes are loaded by using baskets, while the pig iron is transported by a gutter to the furnace, where 3 graphite electrodes apply 140 megavolts of electric energy to melt the load and produce steel, which is emptied into special ladles. In order to produce specific properties, the liquid steel from both systems goes to the secondary treatment station, secondary metallurgy, ladle metallurgy, or chemical reheating. Likewise, liquid steel can be processed in the dual degassing station to reduce the content of hydrogen and carbon for applications with higher requirements. With the treatment completed, liquid steel is transformed into slab on equipment called continuous casting machines. In this process, as it passes through a series of rollers with a cooling system, it begins to solidify until it becomes a slab which is cut with oxygas to the required dimensions. The steel slabs are produced in different thicknesses, widths, lengths, and weights, and each piece is labeled for later processing by hot rolling. The hot rolling department, considered the backbone of AMSA operations, has a hot strip line which produces steel strip coils and 2 plate lines to produce steel plates in sheets or coils. On both lines, the slab is reheated to 1,330 degrees Celsius. Plate line 1 has 2 reversing mills that in a series of passes generate wide plate in the required thickness and width. On plate line 2, the 8-inch slab is laminated in a reversible Steckel mill and the steel strip is temporarily stored in closed box furnaces to maintain temperatures above 1,000 degrees Celsius. Subsequently, an edging mill reduces the width of the strip to produce plate in sheet or coil. If required, the plate goes to the normalizing line, where through thermal treatment a uniform granular structure and greater hardness of the steel is obtained. AMSA is the only manufacturer in Mexico that produces steel plate, which is used for making farming and mining machinery, oil industry machinery, as well as heavy automotive and railway products. On the hot strip line, the slab is processed for the production of hot-rolled coil. First, the slab is reduced in a universal reversing mill to a thickness of 2 inches, and then on the end stand it is further reduced to 1 inch. The final thickness required by the customer is achieved on the 6 standing roll mill train. At the end of the hot strip line, there is a cooling system and a coiler. Hot-rolled coil, also known as full hard coil, is shipped directly to the customer or sent to other processes in the AMSA cold rolling departments. Through cold rolling, the thickness of the sheet is reduced, while at the same time modifying and enhancing its physical properties. The process begins with pickling in order to eliminate oxides through the use of a hydrochloric acid-based solution. Then the strip is cooled to room temperature in various mills in order to gradually reduce its thickness and achieve the desired specifications. In order to soften the material, the coil is annealed in a continuous heating oven at temperatures of up to 750 degrees Celsius. The steel strip then goes to the tempering mills, which give it a greater surface quality and the specified hardness required for the various applications. In addition, AMSA has skin pass and tension leveling lines which improve the surface quality of the hot-rolled and cold-rolled coil respectively. In these units, a greater thickness uniformity is achieved, which is an essential requirement for manufacturers in the automotive industry, home appliances, and electrical steel. Furthermore, AMSA produces tin plate and tin-free steel, which are steels produced primarily for manufacturing of metal containers. In both cases, the cold-rolled coil is subjected to an electrolyte bath with tin and chrome, respectively. In addition to the hot rolling and cold rolling lines, there is a department of structural shapes. AMSA is the primary domestic manufacturer of structural steel for the construction industry. Production begins with the cutting of the steel slab into square pieces called blooms. Reheated in an oven at over 1,250 degrees Celsius, the blooms go through various rolling mill trains to produce structural shapes such as W-shapes, C-shapes, and angled L-shapes. Built on advanced information technology systems, the AMSA productive chain requires support services such as industrial gases, electric power, water, transportation, and maintenance shops. Altos Hornos de Mexico operates its own power plants which use steam and internal combustion engines to...
So, I think you got a very good idea about how things are working. So, you have seen that how ultimately from the iron ores we can produce steel either in the basic oxygen furnace or electric arc furnace, and finally using the continuous casting method through train of rolling mills you can produce the different shape and sizes. Okay, so this thing we have observed that how steel is produced. Now in the continuous casting, if you want to get a better idea, so let's see this video again.
Providing tailored products and services for our engineering challenges. Bloom caster, the low diameter bars. This 200 ultrasonic inspection capability, the ladle departs the vacuum arc degasser after undergoing our specifications. The ladle then travels via transfer car from the ladle area to our new caster building. Once it reaches the caster, a 300-ton crane picks up the ladle. This crane lifts the ladle about 100 feet before placing it on a large rotating turret. Once the ladle is ready to cast, the turret rotates the ladle over top of the tundish. When the ladle reaches over the top of the tundish, a refractory valve opens to allow steel flow from the ladle into the tundish. During this process, a physical shroud and inert gas protect the steel stream from oxidation. As steel flows through the tundish, a series of flow modifiers control the flow, allowing for optimum inclusion flotation and steel cleanness. The steel then exits the tundish to each of the 3 strands. We use refractory stopper rods to control flow from tundish to mold. The mold has a set of 4 copper plates that we clamp together and water cool. Mold powder protects the steel in the mold from oxidation. While in the mold, we utilize electromagnetic stirring to improve the solidification pattern. Below the mold, the cast steel descends vertically with support from a series of rolls contained with 2 segments. These rolls prevent bulging of the bloom surface. Between the rolls, we use air mist sprays to cool the bloom surface and strengthen the solid steel shell. Below the segments, a series of large rolls support the strand. Several of these rolls can apply soft reduction, which is a slight squeezing of the bloom shortly before full solidification. This provides the bloom with a superior solidification pattern and minimizes carbon segregation. After the strand exits the last mechanical soft reduction rolls, we cut it to size using a torch cutting machine. This machine clamps and follows the bloom as it travels to make a straight cut across the bloom face. We can customize the bloom length to allow for optimum cutout in a rolling mill. After the bloom torch cut, a transportation car receives the bloom, raising it to ground level. A longitudinal pusher moves the bloom off the car and onto the discharge table. The blooms then travel to an aerial transfer, which picks up the product and moves it to the cooling bed. On the cooling bed, we weigh each bloom and tag it with a barcode. Finally, we transfer the blooms to a large carrier stand. The bloom then transfers to the rolling mill, where we roll it into bar product. Now you know more about our jumbo vertical bloom caster.
So you got an idea about how continuous casting actually happens. Okay. So here you can see some of the products that we get out from the steel industries, like steel slabs, hot rolled plates, cold rolled coils, hot rolled coils, and you can see hot dipped galvanized coil. Galvanized coil means a zinc coating is given to prevent corrosion. Okay, electro galvanized coil, tin plating coil, that means where tin plating is given again to resist corrosion. Okay, here you can see the blooms. Okay, blooms are basically this square kind of a cross section. Okay, billets are basically the smaller cross sections. Blooms are respectively the larger cross sections. Okay, here these are billets, you can see, and these are reinforcing bar, welded coils. So these are the different kinds of products that we get out of the steel industry. Here you can see different kinds of sections, box, eye, different kinds of sections are also produced. Okay, after this getting an idea about the production of steel, let's see the different kinds of steel one by one. So first start with the plain carbon steel. So according to the definition of American Iron and Steel Institute, that when there is no minimum content is specified for alloying element, that means other alloying element can be even 0%. Okay, so it's plain carbon steel is basically, you just remember, it is iron and carbon is only there. Even if there is no other alloying element present, then it is a plain carbon steel. But some amount of these alloying element may present, and some of the definitions are like this, that when maximum content for any of the following elements does not exceed, like manganese, if it is more than 1.65, we cannot call it a plain carbon steel. Silicon is more than 0.6, we cannot call it plain carbon steel, like that. Okay, or when the specified minimum amount of copper does not exceed 0.4%. So these are the different definitions of the plain carbon steel. But a simple idea, you just remember, plain carbon steel means only iron and carbon is there. Okay, we are not depending on the other alloying elements for the properties of those steels. Okay, so now in plain carbon steel, if it is only carbon present, then what is the effect of the carbon on the steel? So with increasing carbon content in the steel, increases the hardness and strength. That already we have seen in different phase transformation process, different cases, that if the carbon percentage is more, that means it is more hard, that means it is more strong, its tensile strength is high. Okay, decrease in weldability. So this is a negative point. If we increase the carbon, definitely strength increases, hardness increases, which is good, but weldability decreases, its ductility decreases, right? So these are the negative points. Not only that, machinability is also decreases, since with the increase of carbon it becomes very hard, so it is very difficult to machine. Okay, so machinability decreases. Ductility decreases means its toughness will decrease, so which is also not good. Weldability decreases means that you cannot high carbon steels cannot be used for the welding, and for the joining purpose, for structural purpose it will be very difficult. So it is not only the properties. Ultimately, with the help of these materials, you have to create some machine component or structural thing. So for that you have to also remember that what are the manufacturing process through which this material will go through, and if it cannot be machinable, then you cannot give different kinds of shape. If it is not weldable, you cannot produce different kinds of frames or structures. So these are the negative points, and that is why we have to, for selecting certain material, we have to think all these technical properties also, not only the mechanical properties. Okay, here you can see one very good information that 0.2 to 0.25% of carbon, which is basically the mild steel, provides the best machinability. Okay, that is why mild steel is used in such a huge manner in mechanical industry. Now, alloy steels. So in case of alloying, some alloying elements are used to improve certain mechanical properties, okay, or some other technical properties, and these alloying elements are mainly you increase the mechanical properties like strength, hardness, toughness, okay, creep resistance. But creep, probably we have not gone through the creep, but you just remember at this point creep is a very important property which is required for the high temperature application. If the temperature is very high, in that case what happens, that with the increase of time we observe that the deformation takes place. So you are not increasing the stress on it, you are not increasing stress on a mechanical component, but with the time you find that the deformation is continuously increasing, and this particular phenomena is called creep. But this creep happens generally at a very high temperature, like in turbine blades, gas turbine blades. Okay, so creep is a thermomechanical process, but it is a time dependent deformation that occurs. Okay, anyway, for these mechanical properties, to improve these mechanical properties, like to make it creep resistance, to make it hard, to make it uh, high temperature property to maintain, we use different kinds of alloying elements. Now, not only that, we also require some wear resistance property, because there are many components which undergoes a lot of friction and wear may possible. So in those cases, to resist wear, we need the very high hardness, some properties. So by alloying, it is possible to impart those properties. Not only that, corrosion is a big problem. So depending upon the marine applications or some other applications where the environment can damage the material from its surface, so some alloying elements are very helpful to reduce these effects. Okay, so alloying elements are very important to do all this improvement in the properties. Now here you can see the steel can be divided into low alloy and high alloy, that I have already told you. Now in low alloy it can be low carbon steel or a medium carbon or a high carbon. Now you see in low carbon steel it can be either plain carbon steel or it can be high strength low alloy steel. High strength low alloy steel. In case of low alloy steels, where it can be copper, vanadium, nickel, molybdenum, these are the alloying elements, but those definitely will be limited up to very small amount, within 10%, that you know what is the definition of the low alloy. Here in case of a medium carbon, you can see again it can be plain and or some heat treatable alloying elements are also there. Similarly in high carbon, you can see it can be either plain or some alloying elements to improve their properties are added. In case of high, you can see either tool steel or a stainless steel where large amount of alloying elements are present. And here you can see some of the designations are given, and here you can see the comparison of the different properties like hardenability, tensile strength, elongation. These are given here, and you can see as you increase in this direction, that means as the carbon percentage increases, its ductility decreases. Okay, so increasing strength, cost, and decreasing ductility. as you move in this direction. Okay, so here you can see the applications of these, like automotive structural sheets. Here you can see for the low carbon HSLA, that means high strength low alloy steels, where bridges, towers, pressure vessels, this can be used. In medium carbon steel, you can see for the plain one, it is the crankshaft, bolts, hammers, blades, or for heat treatable, it can be pistons, gears, wear applications, okay, where the chances of wear is very large. In case of high carbon steels, here you can see the wear applications, okay. And in case of tool steels, you know, different kinds of tools like drill, saws, dies, stainless steels, you know, mainly for the corrosion resistant applications, high temperature application, turbine blades, okay. There we use stainless steels. Now coming to the gist of what is low carbon steel, what you have to remember, some of the important points I have just shorted here. You just remember these points that contain less than 0.25% carbon. Okay, this is what is the low carbon steel, which is also called the mild steel. Relatively soft and weak, outstanding ductility in the order of 25% elongation, good toughness, also high machinability and weldability. Okay, least expensive to produce, and tensile strength is in the order of 500 megapascal. Okay, whereas in this category, if it is a low alloy steel, that means high strength low alloy steel, here basically contains the alloying element like copper, vanadium, nickel, molybdenum up to 10% because it's a low alloy steel, but it is under low carbon steel. Okay, high strength and corrosion resistance than plain low carbon steels. Okay, and tensile strength can go up to 700 megapascal because you have added these alloying elements, so the strength will improve and it is up to 700 megapascal. Its application like beams, channels, nut bolts, wares, tin cans, etc., where these are used. Now here this is important, high strength low alloy steel, it is basically this one, high strength low alloy steel, also called HSLA, are low carbon steels and small amounts of alloying elements. Why small amount? Because it's a low alloy steels, and these steels contain the least amount of alloying element that still provides the proper yield strength without any heat treatment. Actually, heat treatment is not generally done in case of low carbon steels, and in these steels, careful processing permits precipitation of carbides and nitrides of niobium, vanadium, titanium, zirconium, which provides dispersion strengthening and fine grain size. Okay, so because of this alloying element, what happens? The precipitation of the carbides of these elements actually present in the structure, and those are helpful in providing the fine grain size. Okay, there are two reasons. One is that grain boundary pinning will occur, so grain boundaries will not be very grains will not be very large, and that is why small grain size will be created. That means the material will be strengthened, and so this is the main reason that why with this small amount of alloying elements it is possible to create the high strength. Now here you can see the dual phase steels. It's again a special kind of steel where it is under low carbon steel. This is also a low carbon steel where uniform distribution of ferrite and martensitic structure occurs. Here you can see the ferrite structure and certain martensitic structure is there. With the dispersed martensite provides yield strength in the order of 414 to 1000 megapascal. Okay, these low carbon steels do not contain enough alloying elements. Okay, so that is under low carbon steels with low alloying element. Okay, so a good hardenability using the normal quenching process, because alloying elements are less, that is why the normal quenching process is difficult. But when the steel is heated to the ferrite plus austenitic portion of the phase diagram, the austenite phase becomes enriched in carbon, and which provides the needed hardenability. That means if you remember that portion, okay, so this is say 0.76 percentage of carbon, and suppose you are low carbon steel, so at this level, so carbon percentage is very small, say 0.2%. So now here you see it is basically heated up to this much. If you heat in this region, which is basically ferrite plus austenitic region, and here you see what is the composition of this austenite present here. The composition of the austenite is close to 0.76. That means it is a carbon rich austenite. Okay, so you are getting a carbon rich austenite that is present, and now what is happened, it is cooled very fast from this position. If it is cooled very fast from this position, then that austenite portion will be converted into martensite. But most of the structure in this position is basically ferrite, you can see. So because the opposite term indicates the fraction of ferrite present in the structure, right? If this is R and this is S, the ferrite present is basically S by R plus S, right? That means S portion is very large, so most of the thing is ferrite, and only a small portion which is austenite, but the percentage of carbon in the austenite is very rich, and that is why that austenite will be converted into martensite. Okay, and that is why the structure will be like this. Okay, since dual phases are present, that is why it's called a dual phase steel. Okay, so during quenching, only the austenite portion transformed to martensite. Now coming to another few important grades of steel, like marraging steel. The marraging steel, it is a low carbon, high alloyed steel. Okay, remember it is high alloyed steel, so it is not under low alloy steel. So though we are discussing under low alloy steel, but it is basically the high alloyed steel. That is a portion you have to remember. Marraging steel is a highly alloyed steel, but it is a low carbon steel. Okay, so austenized and quenched to produce soft martensite. Since it is a low carbon steel, so that is why what will happen, even if you quench it, then the carbon, because of the carbon percentage is very low, so the martensite that will form will be very low. If you remember that how with the increase of the carbon percentage the hardness changes, if you remember, it was like this. Okay, it was about 64 HRC hardness value, 64 in C scale, Rockwell C scale. As with the increase of carbon percentage, here it is the carbon percentage, as you increase the carbon percentage, and here in this axis basically it is the hardness of martensite. So this is basically the hardness of martensite in Rockwell scale I have shown here. And you can see when the carbon percentage is very low, like in a case of a low carbon steel, you see the hardness is very low even in the martensite. So it is called a soft martensite that will be produced here where less than 0.3% carbon is present. Now after that, what is done, this martensite is aged about 500 degrees centigrade. The aging is, we have not yet discussed, but basically what is the meaning of it is that you now raise the temperature to 500 degrees centigrade and keep it there for a long time. Then with the increase of time, gradually the precipitation of the carbides will come. What will happen basically, as you are aging, then intermetallic compounds like Ni3Ti, Fe2MO, Ni3MO, this kind of intermetallic phases will precipitate out from the structure. Okay, because carbon percentage is very small, and that is why what will happen, that carbide is not going to come very much, or at a very high temperature the carbides are very soft because they will take a spherical kind of a shape, so they are not going to increase the hardness. But since you are using different kinds of alloying element like nickel, titanium, molybdenum, those are present in this kind of a steel, so what will happen, the other intermetallic phases like Ni3Ti, Fe2MO, these intermetallic hard precipitation will now come into the structure, and they are very hard and not going to melt easily at 500 degrees centigrade. So if you allow sufficient amount of time, a lot of these particles will come into the structure, and the structure will be very, very hard. Okay, so strength can be increased. So this is called the marraging steel. Okay, now marraging steel, the name came because that as if these other intermetallic phases they are present at the same time. Okay, so that is why marraging steel. Now interstitial free steel, these are basically carbides and sulfide formers like niobium, titanium. These are added in the steel. Then what happen? They will form carbide and sulfide, and carbide and sulfide will precipitate, and because of which the carbon that is present in the steel, that will be taken up by the niobium or the titanium. That is why virtually no carbon will remain in this ferrite. Okay, so that is why this kind of steels, which are very formable and very lucrative for the automobile industry. Okay, so this is free steel because it is a carbon free. Because of this, they have strong carbide formers and form this thing. Now another one, which is the keel steel. In a keel steel, basically some deoxidized oxidizing agent like aluminum, silicon, these are used even before casting. Then what happens? They form, they are strong oxide formers, so they form aluminum oxide or silicon oxides, and these aluminum oxides and silicon oxides actually kill the oxygen present within the steel, and that is why the steel casting will be very smooth. Okay, and the blowholes will not be present, and that is why these are called the keel steel, because as if they are killing the all oxygen. And aluminum oxide precipitates and provides additional benefit, and that is the pinning grain boundary. So fine grain structure you will get, and it's a very strong, good structure. You will get a very good strength in this keel steel. Okay. Now here you just see this portion here, some of the plain low carbon steels. Here you can see they are graded like this, and their application like automobile panels, nails, wires, in pipe, okay, in bridges. These are the applications. Whereas some of the high strength low alloy steel, HSLA, here you can see, and their applications are structures that bolted or riveted structures used at low ambient temperature, truck frames, railway cars. Okay, these are certain applications. Now coming to the medium carbon steel. Medium carbon steel, already we know it is the carbon percentage between 0.25 and 0.6. Microstructure, it can be heat treated well, so tempered martensite. Processing, carbon content can be approximately 0.5%, accompanied with increasing manganese, because manganese helps to move the bainite nose so that the quenching and tempering will be easier. Now the properties are stronger than low carbon steel, but expense of the ductility and toughness. So ductility and toughness decreases because the carbon percentage now increasing, so it becomes stronger. Applications, you can see the coupling, forging, gears, crankshaft, other high strength structural components, and steels in the 0.4 to 0.6% carbon range used for rails and railway wheels and rail axles. Okay, this is very important. So finally, what you have to remember for the medium carbon steel, that carbon percentage, okay, and stronger than low carbon steel, low ductility toughness, good wear resistance, and if you see the tensile strength in case of medium carbon alloy steels, you will find that it can be up to 2000 megapascal, or in case of plain carbon steel, medium carbon steel, it is in the order of 850. Application, railway wheels, tracks, gears, crankshafts, etc. Okay. Now high carbon steel. I have already told you it is 0.6 to around 1.2% carbon, with manganese contents ranging between 0.6 to 0.9. Application, high carbon steels are used for spring materials. Okay, for spring materials, high carbon steels are used, and high strength wares, cutting tools, etc. they can be used. And ultra high carbon steel, which is more than up to 2%, say 1.25 to 2%, then some thermomechanical process to produce the microstructure consist of ultra-fine equexed grains of spherical discontinuous product. These can be experimental structures can be prepared, but mostly commercially used are in the order up to maximum 1.2 1.3%. So here you can see what you have to remember finally from the high carbon steels. It is 0.6 to 1.4%, hardest among all these grades of plain carbon steel, strongest and least ductile carbon steel, and can be alloyed with carbon and other metals to form very hard and wear resistant materials like chromium, nickel, tungsten, molybdenum, vanadium. Okay, so applications like cutting tools, embossing dies, saws, okay, concrete drills, these are certain examples where we can use high carbon steels. Now high alloy steels, if we come to the high alloy steels can be of two kinds, either it is a tool steel or it can be stainless steel. Now coming to the tool steels first, where you have to remember these things that commonly used for drill bits and other rotating cutting tools. Okay, it can withstand high temperature without losing its hardness and toughness. This is the most important. At high temperature, the hardness it can maintain. Remember that one of the very commonly used cutting tool material, high speed steel, HSS, where 18% is tungsten, 4% chromium and 1% vanadium, okay, with a carbon content of in the order of 0.6 to 0.7%. Now cobalt high speed steel can also be there, which increased heat resistance, and molybdenum high speed steel, where molybdenum basically can replace tungsten. Okay, also cost effective replacement for the tungsten in tool steel, because tungsten is costly with respect to molybdenum. So molybdenum also having the similar properties like tungsten. Now tool steel, if you see, hardness and simpler heat treatment and retain the hardness at a high temperature. So these are the important properties that you have to remember. The primary alloying element, molybdenum, tungsten, chromium. These are basically the things which having these properties like high temperature, hardness and all that. Now in case of stainless steels, if we see stainless steels, the name itself indicates these are the steel used for the corrosion resistance. That means there will be no stain. So chromium is the major alloying element which is used in the stainless steel, and it is more than 11%. Okay, so along with chromium, what is the other major alloying elements? That is the nickel and molybdenum. So you have to remember stainless steel means it is the chromium maximum percentage, and nickel, molybdenum, these are used. Okay, these are also increases the corrosion resistance, but the mainly chromium. Okay, a property of great importance, the ability of the alloying element to promote formation of certain phases to stabilize it. Actually, since along with the steel you are along with the carbon you are mixing chromium or nickel, because of that basically the whatever we have seen in the iron carbon phase diagram, if you remember, those austenitic region or the ferritic region, those regions actually change. This temperature changes, this composition changes when you are adding the alloying element, that we have already seen. And here is the main thing, the different classes of stainless steel occurs. That austenite forming stainless steel, some of the elements are there which increases this austenitic region to a huge range, or some of the elements are there, some of the alloying elements are there which increases or expanded this ferrite forming region. So for that, if those alloying elements are present, the final structure will be dictated by those, whether it is ferritic or whether it is austenitic stainless steel, like that. Okay, so here you can see the majorly the austenite field can be austenite stabilizers. Those alloying elements are called the austenite stabilizers. Those austenite stabilizers, if present, then austenitic region will be expanded, and in the final structure will have austenite, FCC austenite structure. Okay, whereas some of the structures which contract the austenite region and increases the ferrite region, and those are called the ferrite stabilizer, alpha stabilizers. Okay, so some of the here you can see the austenitic stainless steel, definitely the alloying element that will be present is the austenite stabilizer, austenite field stabilizers like nickel, manganese. If those are present, like copper, cobalt, these are the austenite stabilizing elements. So if these are present, then final structure will be with a larger amount, then final structure will be austenitic FCC structure. And these are the very high quality stainless steels, and corrosion resistance is very high. Final structure is austenite, a bit costly, but very good properties are there. Very good advantage is of all FCC structures: toughness, ductility, creep resistance. So for high temperature application, good wear resistance. And this is a very special kind of steel which is called 18-8 stainless steel. Okay, 18-8 stainless steel. Here you can see where 18%, remember, is chromium and 8% is nickel. Okay, definitely iron and 0.1% carbon is present, but here you can see the main components are 18% chromium and 8% nickel, and that is why this steel category is called 18-8 stainless steel. And this is austenitic stainless steel, that you have to remember. Some of the stainless steels which are ferritic stainless steel, and the ferrite, in case of ferritic stainless steel, actually some of the components like chromium itself is a ferritic stabilizer, silicon, molybdenum, if they are present, they are ferritic stabilizers. In case of, if here you can see one example where 15% chromium is there, 0.6% carbon is present, and this particular stainless steel is ferritic stainless steel. Its corrosion resistance is not so high as you have seen in case of austenitic stainless steel, but they are less costly. Those can also be used for different applications. Okay, but not so corrosion resistant like austenitic steel, but it has again a very good corrosion resistant. Okay, because chromium is there. So finally, what you have to remember, it is that the chromium is the predominant alloy. Okay, at least 11%. 18-8 stainless steel is very important. 18% chromium and 8% nickel. And its application here you can see in cryogenic vessel and different high temperature applications. You can see these are used. The reason that they are excellent corrosion resistance property because of the chromium oxide. Chromium with react with oxygen and produces a chromium oxide layer over the surface, and that layer is impermeable to the further oxidation of the material, and that is why the oxidation of the material does not take place, or the material is safe from the further corrosion. Okay, so that is why the chromium is used for the corrosion resistance. Now, what are the effects of other alloying elements like boron, chromium? So you can see that boron improves the hardenability without loss of machinability. Okay, so this is a very important thing that you have to remember. Here you can see sulfur. Adding sulfur improves machinability. Okay. Here you can see the sulfur improves machinability, wear resistance. Molybdenum improves hardenability and toughness. Nickel, you see, increase strength and hardness without sacrificing ductility and toughness. So very important. Okay, because when nickel is added, then toughness or the ductility can be increased. Even if you are increasing the strength, generally what happens, if you increase the strength, then toughness or the ductility decreases, but the nickel maintain its toughness or ductility along with increasing strength. It's a very important quality. Vanadium, excellent alloying element. You can see it can increase strength, hardness, wear resistance, high temperature, shock resistance. Lot of advantages there. Vanadium, excellent alloying element. Titanium improves strength, deoxidizes steel. Okay, so you have to remember this important major alloying elements effect. Okay, now here you can see a relative comparison among the different alloying elements. See, hardenability, high temperature, strength, ductility, toughness, all these alloying elements having these properties, but the relative effect you can see over here, that hardenability, almost all the alloying elements, you can see increases hardenability. But if you compare, you can see with respect to nickel, they have the higher hardenability. High temperature strength, you can see that high temperature strength, these are having vanadium, tungsten, okay. Nickel, they having the high temperature strength property. Similarly, ductility and toughness, you can see in case of nickel having excellent toughness property. Manganese also having that. You can see wear resistance. Tungsten is excellent wear resistance along with titanium, vanadium, others. Promote fine grain size like vanadium, titanium. Fine grain size means a kind of increase of strength. Corrosion resistance, chromium is maximum, molybdenum and nickel is also. So remember, hardness is a material property that we know, resistance to penetration or scratching, but hardenability is the way to indicate a material's potential to be hardened by heat treatment. Hardenability we have explained in the phase transformation in detail. Now steel, coming to the cast iron portion. Okay, as you know, the ferrous materials can be divided into steels and cast iron. So now coming to this region, cast iron. What are the different types and their properties and application we see. Now cast iron is basically what we have seen, it is more than 2.1%, but more commonly the cast iron is between 3 to 4.5% carbon, which is practically used. Why these are suitable for the casting purpose? Because they are having the low melting point. What is the melting point of the cast iron? That you can get from the phase diagram, close to 1200 degrees centigrade. You know the eutectic temperature is only 1147 degrees centigrade, right? If the carbon percentage is less than the eutectic, it will be slightly more. But in comparison to steel, the melting temperature is quite low. That is why easier for casting. Now cementite decomposes to ferrite and graphite. So this graphitization process, that Fe3C, is actually a metastable phase that is present in the phase diagram we have seen. If you allow sufficient amount of time, that means if the cooling process is very slow, and if the alloying element like silicon is present more than 1%, if the generally silicon present forming this, if it is more than 1%, then this Fe3C transformed into ferrite and graphite. Okay, so graphite is formed. So in cast iron structure, basically it is graphite is present in most of the structures, and some special kind of cast iron where cementite may present, like in white cast iron. Anyway, let us see which portion we are talking about in cast iron. It is 3 to 4.5, so that means this region. Okay, and there are different kinds of cast iron like grey cast iron, nodular cast iron, white cast iron, malleable cast iron, okay, compacted graphite iron. So let us see one by one what are the different types of cast iron. Here you can see the first one is the grey cast iron. Okay, grey cast iron, what are the properties? The carbon percentage between 2.5 to 4%. Graphite exists in the form of flakes. So in the cast iron already we told that Fe3C actually converted into graphite flakes. So in grey cast iron, basically silicon is present in the order of 2 to 3%. 2 to 3% silicon is present. And since 2 to 3% silicon is present and the cooling process is very slow, and that is why what happens, the Fe3C transformed into graphite flakes. So silicon actually helps in converting cementite into graphite flakes. So in the structure, you can see the graphite that is present in the shape of flakes. So graphite flakes having self-lubricating property and vibration damping capability. These are two very important properties of the grey cast iron. Self-lubricating properties, because since the graphites are in the form of flakes, so one layer can slide over the another one. So that is why it has this self-lubricating property, and that is why you will find that when you are trying to machine a grey cast iron component, you do not need any coolant, because coolant doing a role of lubrication, and that is not required in case of a grey cast iron machining. because gray cast iron having this self-lubricating property. Another very important property of the gray cast iron, that is the vibration damping capacity. The vibration damping capacity is very high in case of a gray cast iron. Look at this diagram. Here, suppose some mechanical vibration is initiated, and you see that particular disturbance will die out in case of a steel after a very long time. Okay, whereas in case of a gray cast iron, you see it's damping out within a very short period of time. That means it has a self-damping or vibration damping capacity is very high, and that is why the gray cast iron is preferred for different machine bases. Okay, forming of different, suppose you have seen the lathe machine or a shaper or a milling machine. During the machining operations, you know that a lot of vibrations are generated, and if the vibrations sources are present, then if the vibration happens, then what will happen? Ultimately the job surface will deteriorate. So that is why the bases are produced of all these machine bases are made with the gray cast iron, so that the damping effect will be highest. Okay, so the vibration will not be felt much. So the base structures for the machines and the heavy equipments are made of gray cast iron. Tensile strength, you can see 120 to 280 megapascal. So strength and ductility are much higher under compressive loads. So gray cast iron, these kind of materials are generally can take huge amount of compressive load, but do not take much tensile load. Okay. Now here you can see this is the white cast iron, and white cast iron there is no graphite present. That means the cooling process is very fast. If the cooling process is very fast, then what happens? This cementite will not get any time to diffuse this carbon out as a form of graphite, and that is why white cast irons are produced when you are cooling it very fast. Okay, and silicon is not present. So in the final structure, the cementite is present. Okay, in the form of carbides, and formed by rapid cooling molten iron. So you can understand the cooling rate is very high, and that is why graphitization not occurred. Very hard and wear resistant, corrosion resistance. Generally not suitable for any particular use, but since they are very brittle, very hard materials, but suitable for rollers in the rolling mills. You have just seen in the steel making process, a lot of through the hot rolling mills, through the cold rolling mills, the steels are passing, where there are chances of lot of corrosion at a very high temperature, lot of wear, because they are continuously rolling over the surfaces of the steels or some other materials to reduce their sizes. So they has to be very hard, and their shape should not be changed. Okay, so that is why they should be made of a very hard materials, and white cast irons are used in those rollers. Okay, now coming to the malleable cast iron. To form malleable cast iron, initially the white cast iron is first prepared, and then this white cast iron is then heated around 800 to 900 degrees centigrade for a prolonged time, more than maybe 30 hours. Okay, and then they are cooled. Okay, and depending upon the cooling rate, the structure can be different, but finally when you are cooling it, then the structure that you are going to get, it forms graphite, but in the form of clusters. These are called the rosette structure. Okay, so this clusteral structure you will get of the graphites, and these are respectively very malleable material among all the grades that you have seen. Malleable means you can hammer it to a very small thickness. Okay, tensile strength is respectively high, highly shock resistance property, tough material, and an applications is like in connecting rods, in transmission gears, and differential cases for the automotive industry, flanges, pipe fittings, valves, parts, they are made of malleable cast iron. Now coming to the ductile cast iron. Okay, or this can also be called nodular cast iron or spheroidal cast iron. So these are the cast irons when in presence of magnesium, this particular catalyst helping to form this nodular shape or the spherical shape. Magnesium 0.1 to 0.8% are present, and then if you cool it, then you will get this particular nodular or spherical structure. Okay, so in presence of silicon, what we have seen in case of a gray cast iron, in presence of more than 1% silicon, the graphite takes the shape of flakes. In presence of magnesium, 0.1 to 0.8%, it takes the shape of nodules or the spherical shapes. Okay, and you can see they having high fluidity. The tensile strength is also very high, tough and wear resistance, good machinability, weldability. Okay, so these are designated like SG902, where this 900 indicates the tensile strength and 2 indicates the percentage elongation. Okay, so this is what is the spheroidal cast iron. Now compacted cast iron, you see, where the product is in between the gray and the ductile cast iron, and carbon partly filled and combined form. The graphite has like worm-like structure that you can see over here, better resistance to thermal shock, lower oxidation and elevated temperature, application like diesel engine block and all that. Okay, so we have seen some of the different structures of cast iron and their properties, and now let us see the important alloying elements in cast iron. Like silicon, already you have seen, if silicon is present, then it forms the graphite in the form of flakes. Okay, makes the iron soft and easily machinable, produces sound casting, free from blowholes, and having high affinity for the oxygen. So silicon having the high affinity for the oxygen. Now sulfur. Sulfur makes the cast iron hard and brittle, and above 0.1% makes unsound casting. Manganese makes cast iron hard by forming of carbides and keeps control over harmful effects of sulfur. And phosphorus imparts fusibility and fluidity but induces brittleness. These are certain important alloying elements. Now if you just try to see the phase diagram again and see the processes by which the all kinds of grades of cast iron that we have just seen. Now see, suppose you are at the liquid condition and from that you are cooling it, and during this cooling process, depending upon the cooling rate, how you are getting the different structure. You see, if your cooling rate is very fast, that means if you cool it very fast, then what will happen? This final structure here will be pearlite and Fe3C. Okay, this is very simple because here you can see basically austenite will be there and Fe3C will be there, and since you are cooling it very fast, maybe the pearlite will be there and Fe3C is not going to produce the graphite because you are cooling it very fast. So final structure will be pearlite and Fe3C. Maybe if you cool it very fast through this region, even that formation of pearlite may not be possible, and ultimately it can form martensite. That is also possible. Okay, it all depends upon the cooling rate, because austenite, if you cool it very fast, then it can form the martensite also, or if you control ostempering, then bainite structure also can be formed. So it depends everything on the cooling rate. Now if you cool it moderately, then what will happen? Since you are cooling it moderately, that means you are giving sufficient time, then pearlite structure will be there, and along with the austenite now comes in as a graphite flakes. Here you can see it will become graphite flakes. F indicates the flakes. And if you cool it very slowly, then what will happen? Even from in the pearlite structure, what is there? It is basically alpha ferrite and Fe3C is there. But if you cool it very slow and if silicon is there, then that within the pearlite structure, that Fe3C will even converted into the graphite flakes. So under very slow cooling, what will happen? Final structure will be ferrite and the graphite flakes. Now if you see, if you add magnesium or cerium in the structure, then what you will find? Then in presence of magnesium, you know that final structure will be again pearlite and graphite, but now the graphites are not in the form of flakes, in the form of nodules. Okay, so this is N indicates the nodular shape or the spherical shape. So pearlite plus graphite in the form of nodules. But if you cool it very slow, again what will happen? from even within the pearlite, the cementite that is present within the pearlite, that will transform into ferrite and graphite nodules. So final structure will become only ferrite and graphite nodular structure. Now you see this structure you already know is the white cast iron. Okay, and this white cast iron, if you heat it,